So today we're going to talk about stable isotopes. And hopefully by the end of the lecture, you'll be standing upright in the barrel instead of upside down in the barrel in terms of your understanding of isotopes, or at least how you feel about your understanding of isotopes. So we're going to talk about, we have an introduction, talk about what an isotope is, how isotope ratios change, in other words, how they fractionate, which is what we call it. We're going to talk about oxygen, carbon, sulfur isotopes as examples of stable isotopes, and then copper and thallium as examples of non-traditional isotopes within sort of ore deposit studies writ large. So we can think about the three axes of a sample. We can talk about its composition, how much stuff is in there, and we use a variety of analytical instrumentations, which are listed there: ICP-MS, ICP-OES, XRF, electron probe, microanalysis, etc., to tell us how much. We can use instruments like XRD and scanning electron microscopy and Raman spectroscopy to tell us what the sample is composed of, what minerals make up that sample. And then finally, we can use mass spectrometry to analyze isotopic compositions. What is the source or the origin, the fate of metals as they move from where they start to where they're deposited in a mineral deposit to how they migrate afterwards as we modify that mineral deposit. And so what's an isotope? Isotope is the same place, i.e. in the periodic table. So if we consider hydrogen, hydrogen has an atomic number of 1, and that does not change, but its atomic mass at the top left here, that can change. So hydrogen 1 has 1 proton and no neutrons and 1 electron. And we can call that protium or hydrogen 1. So it has an atomic mass of 1 and an atomic number of 1. We then go to deuterium, which is also called heavy hydrogen. And this has got a atomic number of 1 because it's still hydrogen, but it has a mass number of 2 because it has 1 proton and 1 neutron and 1 electron. And neutrons and protons weigh about the same. And then tritium, which is radioactive, has 2 neutrons and 1 proton. So it has an atomic number of 1 and atomic mass of 3. So there's a large and growing number of isotope systems that have been applied to the study of the formation of and exploration for mineral deposits. And we can break those down into 3 broad classes: radiogenic isotopes, traditional stable isotopes, and non-traditional stable isotopes, although I don't think anyone agrees at what point a non-traditional becomes a traditional. But anyway, that's a discussion for a different time. And so there's several different ways that we can use isotopes in terms of understanding ore deposit formation or mineral exploration. We can use radiogenic isotopes to date the age of mineralization or the footwall host rocks. We can use isotopes as indicators or vectors to mineralization, where there's a clear isotopic contrast between the ore deposit or what's anomalous and the surrounding rocks, or as indicators of water source, water age, water rock interactions, and that sort of thing to help us improve our understanding of the system as a whole that's under study to help us build better exploration models and so forth. And so this is just a periodic table of the elements showing how many stable isotopes there are for each element. This is not to say that there's not a lot of unstable elements. So gold, for example, has only 1 stable isotope, but it has lots of radioactive isotopes which have very short half-lives, and so we don't consider those. The isotopes that are unstable, which we do use in geochemistry, are uranium and thorium, primarily down here. So basically what we can see is that elements with only 1 isotope are not of much use in isotope ratio analysis. What we want is 2 or more. And we use the delta notation to report our data. So let's consider the isotope ratio of carbon-13 to carbon-12. The heavier isotope typically goes on the top, and the lighter isotope typically goes on the bottom, and that's typically the most abundant. And we measure ratios because we can measure them very precisely. But the numbers are very small. And so what we do is we use a delta notation where we're multiplying things by 1,000. So for example, if we take the isotope ratio for hydrogen, that is hydrogen 2 to hydrogen 1, it's simply a ratio of hydrogen 2 over 1 in the sample divided by 2 over 1 in the standard that we have, minus 1, and then times 1,000. And the times 1,000 is just to make nice big numbers that we can deal with. And then we report those delta values in units of per mil, which is like saying percent, which is per 100, but this is per mil or per 1,000. And so how do isotopes fractionate? They can fractionate by kinetic and equilibrium fractionation processes. They can fractionate by radioactive decay, which is time. And Bob's going to talk about that later on. And then we're not going to talk about mass-independent isotope fractionation. That's becoming an increasingly important area of study for understanding how the Earth has changed through time and various transformations in the atmosphere and biosphere and things like that. So it's important to note that only radioactive decay results in the change in the amount of an isotope in the Earth, whereas all the other fractionations that we're talking about redistribute the various isotopes among different phases. Okay. And so we can have kinetic and equilibrium fractionation, which are the two most important for my lecture. So kinetic ones tend to be rapid and non-reversible. They commonly result in large fractionations, so large changes. So we can have evaporation, biogenic processes, diffusion, redox changes. And the light isotope tends to go to the more kinetically favorable state. Bacteria love light isotopes. We can have reversible, equilibrium could be reversible. Fractionations are normally smaller. And so these are things that tend to happen at higher temperature. So in sort of a basic sense, heavy isotopes form stronger bonds than light ones, so they're harder to break. That's why bacteria love light isotopes. Heavy isotopes tend to concentrate in phases with stronger chemical bonds, and this effect is reduced with increasing temperature, as all phases become more similar in their isotopic composition as we increase temperature towards magmatic values. So here we have a nice XY plot showing fractionation on the y-axis in per mil. So that's our delta notation. And on the x-axis is the mass difference between the two isotopes. And so you can see hydrogen's not on that because there's a mass difference of 100%. And so what can we see? We can see that isotopes or elements like nitrogen, sulfur, carbon, oxygen, which are sort of the traditional isotopes, as well as boron and selenium, these are all redox sensitive species. And so they tend to have very large fractionation factors, and they have fairly large mass difference. Generally speaking, as we increase the atomic weight, the mass difference gets smaller, and so the fractionation gets smaller. To look at it a different way, so on the y-axis now is the range of values that we might find in nature for a particular isotope system, and on the x-axis is the atomic number. And what we see here is that as we, which I already just said, but it's sort of shown better graphically, as we increase the atomic number, we decrease the extent of isotope fractionation that is typically found, with the caveat that these heavy isotopes, mercury, thallium, and uranium, can have large fractionations because they're very redox sensitive. So I should point out the blue diamonds are redox reactive species. The orange diamonds are non-redox reactive in most geological systems, and the red outlined ones are the traditional stable isotopes. Okay, so in terms of nomenclature, so on the y-axis we have the delta symbol, or per mil, and we talk about isotopes being enriched, or if we're talking about delta 18O, which is the isotope ratio of 18 oxygen to 16 oxygen, if it's a high value, we call it enriched, or heavier, or higher, or positive. And on the right hand, we can see that felsic rocks tend to be heavier or more enriched than the standard. mantle is slightly less enriched compared to the standard. If it's negative values, we could call them depleted, lighter, lower, or negative. So rain in Dallas is less than the seawater standard, and snow at the poles, as we'll see in a minute, is even more negative. Okay? So that's relative to any given isotope standard. In the case of oxygen and hydrogen, we use seawater as the standard. So I just have one slide on how isotopes are measured because I teach a whole course in this, but we can have TIMS, which is thermal ionization mass spectrometry. We have SIMS, secondary ion mass spectrometry, multi-collector ICP-MS, so multi-collector inductively coupled blah, 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 blah. You don't need to know that, the acronyms. We can have ICP high resolution mass spectrometry or isotope or quadrupole mass spectrometry, IRMS, AMS. The point here is that they are all mass spectrometry because we need to measure isotopes at different masses because of the different number of neutrons. The image at the bottom there is the AMS. It's the only one in Canada. It takes up the entire floor of a building. There's a massive periodic table on the ground on the floor there. It's a spectacular periodic table, and it's got all the unstable isotopes on it as well as the stable ones. Spectacular. So, what isotopes serve utility in mineral deposit studies? So Bob's going to talk about the radiogenic isotopes. The image just shows what happens when we have alpha decay. An element loses a helium ion, or helium atom, sorry. 2 neutrons, 2 protons. And so the mass number changes by 4. So samarium-147 would decay to neodymium-143. The image on the right is showing what happens in beta decay. In beta decay, a neutron gets converted to a proton, and the nucleus spits out an electron. So this is not an electron from the cloud around the nucleus. This is an electron expelled from the nucleus. And so, for example, we convert rubidium-87 to strontium-87. And so what we see is there's no change in the mass number, but there's a change in the atomic number, which is cool. Okay, then we have the traditional stable isotopes, commonly referred to as the light stable isotopes. They're non-radiogenic, have low mass, and high mass differences between the isotopes. And they're more readily fractionated by surface processes, such as by temperature, biological activity, adsorption onto mineral surfaces, water-rock reaction, redox reactions, and mineral precipitation. And so traditional ones would be oxygen, sulfur, hydrogen, and carbon, but you could include helium, boron, silica, chloride, and lithium in there, which are being used quite a lot. And then we have the so-called non-traditional isotopes, and these are called non-traditional because they're relatively new in terms of understanding the controls of fractionation and so forth. And so you'll see a lot of papers in the literature now trying to apply these isotopes to different systems to see how they're fractionating in nature. So let's move on to oxygen isotopes. So the image just shows the water cycle, and the reason for showing the water cycle is the water cycle. Water is made up of dihydrogen monoxide, aka H2O. And so we have hydrogen and oxygen isotopes, and we're just going to talk about the oxygen, but they're moved throughout the water cycle, and they can fractionate as a function of a variety of processes, fundamentally related to temperature. And so we can see evaporation off the ocean. We can see precipitation from clouds. We can see condensation and recharge and high elevation recharge and low elevation recharge, sublimation of snow, groundwater interaction, etc. Right? So all of these different parts of the cycle result in fractionation of oxygen isotopes. And so we can talk about what processes result in these variations. We can talk about what the ranges of oxygen isotope fractionation are, and what do they tell us about geological processes in ore-forming fluids. And so let's dive in. Okay, so one of the things that oxygen isotopes do is they fractionate as a function of rainout, or temperature. So what this means is that we move from left to right across the diagram. On the left-hand side, we've got the ocean, and because ocean water is our standard, oxygen 18O, which is the ratio of oxygen 18 to 16, has a value of 0 per mil because it's the same as the standard. Now, when we evaporate, the lighter oxygen 16 to hydrogen bond is weaker than the oxygen 18 to hydrogen bond in water. And so as a result, when we evaporate ocean water, we end up with water vapor, which has negative oxygen isotope values. So in this case, in this example, minus 12 per mil. All right, because we've preferentially taken the light isotopes out of the ocean water and made water vapor. All right. Now, then when we condense that to form clouds, and then the clouds rain, it's easier for the heavy oxygen, oxygen 18, to form bonds with hydrogen. And so the rain will be relatively heavier in terms of isotopes. So we started with water vapor at minus 12 per mil, and the rain will have a value of minus 3 per mil because it's taking out the heavier isotopes, right? So it's becoming more positive. The result of that is that the remaining water vapor after we've had a rainfall event becomes even lighter because we've preferentially taken out the heavy isotopes. And then if it rains again higher up in elevation, that same process happens. Now the rain has a isotope value of minus 11. So it's more negative than the first rain because there's less heavy isotopes by the time we get to that second round of precipitation, and so on. And this process repeats itself. And so as we move from the coast inland in a continent, the isotope rate values become increasingly negative or increasingly lighter. And so we can take waters anywhere in the world, rainfall or snowfall, and in most cases, they're going to fall right along this line. And this line is the hydrogen isotopes. So this graph is hydrogen isotopes versus oxygen isotopes. Standard mean ocean water, or our standard, is up here at 0, 0. And this line was recognized by this scientist called, I forget his first name, Craig, and he published this in 1961, and he called this the global meteoric waterline.
Oh, that's Harmon Craig, very famous
Harmon Craig,
geochemist and a significant character who used to keep his PhD students in the lab for much longer than 5 years.
So there wasn't a lot of harmony.
Oh, yeah. Good one.
Thanks. So that's interesting. So we call this the global meteoric waterline, and it has an equation of 8 times the oxygen plus 10 per mil gives us the hydrogen isotope value. And what you notice is, as we go from the equator to the South Pole, the values get more negative. So this is the latitude effect. So as we get higher and higher latitudes, we get more and more negative values. Why? Because it's colder towards the poles. So temperature is a fundamental control on oxygen isotope fractionation. So most geoscientists, who are concerned with Earth evolution, the most critical aspect in isotope hydrology is temperature. So why do the hydrogen isotopes correlate with each other and with temperature? So again, the global meteoric water line is delta 2H or delta D equals 8 times the oxygen isotope value plus 10. And so Dansgaard, who I also forget his first name, but I'm sure Bob knows it, found 4 factors that determine isotopes in precipitation. There's the altitude effect, the distance from the coast, which is also called the continentality effect. There's the latitude effect, so how far north or south you are. And then there's the amount effect. So the amount of rain, so in really heavy rainfall, you'll get less internal fractionation than you will in an arid area where you might get evaporation during rainfall, which will fractionate the isotopes. And so this is a map taking all those effects and plotting it on the globe. And what do we see? We see that at the equator with the hot colors, the red colors, That's where there's very little isotopic difference in oxygen 18 compared to the standard. And as we move to the poles, we get more and more depleted or much lighter isotope values. So as we get to the very tip of the North Pole, we have values lighter than -30 per mil. Not so much data on the South Pole. It doesn't rain or snow very much down there.
Sorry, Matt.
Yeah.
I was just wondering, where are these samples taken from that are on this map?
Yeah, so that's a great question. From the literature and from the IAEA there's a bunch of monitoring stations all over the globe. And all of this data is actually freely available through the IAEA, which is the International Atomic Energy Agency. And so you can download precipitation data for anywhere in the world and develop your own meteoric waterline for a particular study area. Yeah, it's a great question.
I think Madison's got a question.
Yeah, so if the evaporation is preferentially selecting for the lighter isotopes, do we see an increase in the heavier isotopes in like the surface waters, especially kind of anywhere along the coast that's getting that heavier precipitation, or is it too subtle of a difference in the like scale of the ocean to be measurable?
Right. So the ocean is extremely well mixed with respect to oxygen and hydrogen. So you don't see, and it's such a large reservoir. Yeah, you don't see much fractionation. You would in restricted lagoons and things like that. Is that what you mean? Yeah.
It'd be interesting to look at something like the Dead Sea, where the evaporation is so high.
Yes.
You can imagine there would be a huge fractionation between Jordan River water, which looks like it would be about -6 or something, and the Dead Sea water, which should be heavier.
Yeah.
Right.
Yes.
But
well, if we go back to this map, you can see closed basins tend to be very isotopically heavy.
Yeah.
Which the Dead Sea would be one.
Yeah, it's about as closed as you can get.
Yeah, in more ways than one. But anyway, we won't go there. Okay, so on the left-hand side, we have our hydrogen versus oxygen isotope plot. And we have the meteoric water line shown there with Craig's value. And it also shows the latitudinal shift. So as we get to low latitudes, we get heavy, and if we get to high latitudes, we get light. The other thing we have on here is we have a field for metamorphic fluids and a field for primary magmatic water. Now, that doesn't mean that all magmatic water plots in that box. It's just a propensity. And we also have these fields for different sedimentary basins. And so what these sedimentary basins represent is mixture between meteoric water at the meteoric water line and some ancient evaporated seawater. And so that these become mixing trends. And the point here is that primary magmatic water is off here to the right, so it's isotopically heavy. So if we had a meteoric water or seawater interact with magmatic rocks, we would expect a trend going out to the right. And we see that in the Salton Sea, and we see that at Steamboat Springs in Nevada. These are geothermal fluids. So what that means, we look on the right-hand side, we have a series of oxygen isotope values for different ore deposits. And so we have the oxygen isotope value on the y-axis, and on the x-axis, we go away from the deposit, into the deposit, and then away from the deposit again. And so the most altered, you can see there's a reduction in the oxygen isotope value, right? Because it's being pulled towards seawater values. Okay.
So that's worth exploring a little bit more. So, like the origin of the fluids that's responsible for the alteration is the question. So now, when you're standing around a ore deposit, the rocks around you are altered. They're not even rocks in most cases. It's kind of junk, and But the question is, what was causing that alteration? And by doing this kind of work, you can figure out, was it groundwater or that kind of water, or was it magmatic water or a mixture?
Yeah.
And the interesting thing is that in order to know what the groundwater was, you have to know something about Dansgaard's rules. And by the way, I don't know what the first name is, but I'm sure it's something Norwegian or Danish or something, right? But Madison's got another question.
Yeah, I was curious about the difference in the isotopic composition of magmatic water. Is that, I guess, how have we measured that? And is it really consistent kind of globally, or is it not more kind of location specific when you're doing these calculations?
So that's a really interesting question. And so the values change as a function of where those magmas came from. So we can get magmatic water values from geothermal fluids and that from degassing magma chambers. We get the values from magmatic rocks by measuring the rocks directly. And mafic rocks tend to have oxygen isotope values of around 6 per mil, so around about here. And felsic rocks tend to have values closer to 10 per mil, okay, because they're more fractionated. So as Bob's saying, that it's the nature of the fluids doing the alteration. It depends on where that originates on the meteoric waterline, because most hydrothermal fluids, I should say the plot on the right is for volcanogenic massive sulfide deposits, which we're going to learn more about in subsequent lectures. But in those cases, most of the fluid is modified seawater, and it's been modified by interacting with rocks. And then as it heats up, it's going to trend more and more towards the primary magmatic value. And so the more altered the rocks, the more that the more seawater that's fluxed through the rocks, so the greater the water rock ratio, so the lower the isotope value will be in terms of oxygen isotopes. So the higher the alteration, the lower the oxygen isotope value will be.
Well, it's even more complicated than that, because that is the alteration that happens at the time of mineralization. And the diagram you're looking at on the left, in many ways, is what happens to the deposit after it's exposed to processes in the critical zone with groundwater. So it gets real confusing real fast.
It can get very confusing. However,
yeah, I have a quick question.
Sure.
Relating to how it get confusing, or another layer, because wouldn't it be due to the state of the water at the time of mineralization, which might not either for seawater or for magmatic water match the measurements we have today?
So seawater hasn't really changed its composition through time, not by very much. And magmas, especially from the mantle, they're pretty uniform. And so when we mix those fluids, we're going to get some kind of mix in between.
Okay, those have been consistent even on geologic timescales?
Yeah.
Oh, cool. Thank you.
Okay. So, as Bob said, it's very complicated, but what we can do is we can take that plot on the right, and we can take that concept that we get a change in the isotope value as a function of water-rock reaction, hydrothermal fluids interacting with the rock, changing the isotope composition, and we can use that for exploration. So here is a map, and this is of the Kidd Creek deposit, which is in Canada. It's in Ontario. And so what we see some black dots here, which represent some of the VHMS, or volcanic hosted massive sulfide deposits, or AKA VMS. So these deposits that form on the seafloor. And we can see the big dots represent more than 2 megatons, and the little dots less than 2 megatons of ore. And so the chart has been color coded. So someone did a survey, analyzed a whole bunch of whole rocks, and measured the oxygen isotope values. In the pink, it's more than 9 per mil. In the blue, less than 6 per mil. So if we go back to here, we're going from sort of 9 per mil down to 6 per mil. We're even round about here. And so what you can see is that where the big deposits, we tend to be close to those depleted or lighter values of less than 6 per mil. So you could use this as an exploration tool. You could go out to an area, measure a whole bunch of oxygen isotopes, look for depletions in oxygen isotope values, and then say, okay, let's drill a hole. That would be one approach. People have also looked at oxygen isotopes in carbonate rocks. So if we look at the image on the right, and this is for, this study was done in Nevada and Carlin type deposits. And I think in the syllabus, Bob had a video on Carlin type deposits that you could look at. But the core on the right and the left, so these two cores, they look visually the same. And yet when the people who did this study, which is done at Mineral Deposits Research Unit at University of British Columbia, what they found was that if they looked at the oxygen isotope values of the carbonate minerals in the whole rock on the left-hand side, they gave a value of 26 per mil. And the ones on the right gave a value of 15 per mil. Well, background carbonate rocks have 26 per mil. The rocks near the ore deposit had lower isotope values. So even though the core looked the same, one in some areas they were isotopically changed. So the cartoon on the left is how they perceive this going on. So in this cross section, we have the black represents ore, the orange represents visible and geochemical alteration. So there might be changes in gold concentrations, thallium concentrations, and things like that. So elemental changes or anomalies in concentration. But then the yellow gets even further outboard of that ore system. And this is the cryptic or isotopic alteration. So there's no geochemical evidence of alteration, but there's an isotopic evidence of alteration. And so if you drilled a hole, so up here on the top left, there's a drill rig, and they've drilled a hole down into the system, and they've intersected these isotopically altered rocks, well, that would be an indication that maybe we should look somewhere along axis, along strike of these particular anomalies to see if we can find an ore deposit. And so this is sort of a real example from Nevada. And I think it's called the Screamer deposit, I forget. But this is just a surface map, different geology, which is not really that important. And what you see is a series of drill holes in a line. And so we're going to look at those in cross section. And so here's the geology in cross section. So these are gold deposits in Nevada. And what they did was they did a whole bunch of oxygen isotope analyses and gold analyses and samples from all these drill holes. So if we go to this one, SW, which is well outboard of mineralization, you can see there's no gold. Gold is the lighter symbol and refers to the top axis. And the oxygen isotope values, notice that the bottom value on the x-axis is going in reverse. So it's going from heavy to light. So the oxygen isotopes are quite heavy, which is what we saw here, quite heavy for the unaltered. And as we come into the system, you see the gold concentrations go up. So we start seeing spikes in gold in these two drill holes and in this one over here. And convert at the same time, or in the same samples, what we see is the oxygen isotope values become lighter. They move to the right. So that's just suggesting that, yes, we could use oxygen isotope values as an indicator of mineralization. And so we can plot all that data up in a bar chart, box and whisker plot, and the holes that were in the ore zone have, on average, lower oxygen isotope values. You can see the means go down. So that the line in the middle of the box is the mean or the median, and it goes down and then up again. So, and the red square represents gold greater than 0.2 ounces per ton or 0.2 grams per kilogram. Okay, so very quickly, just a couple of slides on carbon isotopes. And the reason for that is carbon isotopes are really, really complicated. And they're complicated because obviously carbon makes up life, at least life on this planet as we know it. So there's three main isotopes of carbon. There's carbon 12 and 13, which are both stable isotopes. And then there's carbon 14. So they all have 6 protons. They have 6, 7, and 8 neutrons respectively. Carbon 14 is radioactive, so it's unstable, and it has a half-life or decay. 50% of it will decay in roughly 12,500 years. So I'm sure most people have heard of carbon 14 dating. It's good back to about 50, 60,000 years. The chart on the bottom just shows some of the range in carbon isotope values for different reservoirs. And you can see meteorites have quite a large range. The atmosphere is quite restricted. The ocean is around 0 per mil. Limestones, because they form from ocean water, there's not much fractionation. They have values similar. Freshwater limestones, so they form from groundwater, which is isotopically lighter. So they're lighter. And then we have really large ranges for things where there is biological activity. Okay. And then igneous rocks have values that are roundabout mantle values, around -6 per mil. And so there's not been a lot of case studies of using carbon isotopes in mineral exploration or ore deposit studies, but this is one that I found. The dots on the map represent the carbon isotope values. So the little dots are very negative. The big purple dots are the most positive. They're still negative, but they're the most heavy. And the shading underneath represents it represents the guess it's ore values. Anyway, it's not really important. What's important
Looks
is
like del 13
it could be the
per mil.
Yeah, it could be.
That's what it seems to be.
Yeah.
I guess they're
So
just
it's just a map. Yeah, it's just a map
yeah.
showing the same data. Yeah, you're right.
Yeah.
Should have known that. But what we see is the ore deposit symbols here. And so there's some deposits with the triangles and then other showings with the hammers. And we can see that the heaviest carbon isotope values are surrounding some of these ore deposits. And so the idea here was that, again, in surface samples, it might be useful to vector to mineralization. Okay, and then a little look at sulfur isotopes. So there's 4 main isotopes of sulfur, 32, 33, 34, and 36. Normally what we measure is the ratio of sulfur 34 to sulfur 32 because they represent the most abundant isotopes. So sulfur 34 is about 4%, and sulfur 32 is about 95% of the sulfur in our environment. There are these 2 minor isotopes, 33 and 36, which are increasingly being used, but we're not going to talk about those because it's more complicated. And so this is just a image of the sulfur cycle. And the important point to take home here is that we have different forms of sulfur in different reservoirs. So in the oceans are nice and oxygenated, at least in most of the world's oceans. And so sulfur is there as sulfate. And if you think about the math there, so there's 4 oxygens, it's 2 minus, so sulfur would be in a 6+ state. Volcanoes and sulfur from combustion of fossil fuels have SO2, so slightly more reduced sulfur. And then if we look at sulfur in living organisms in seafloor hydrothermal systems, sulfur is there as H2S, or -1 and -2 states. Okay, so point being, sulfur is highly redox reactive, and as such, can have large variations in the isotopic compositions. So what do we use sulfur for? We can determine the source of ore components. We can understand the chemical composition of ore-forming fluids. pH and EH are really important, and that's because sulfur is redox reactive, as we talked about redox last time. So then we can look at the differences in sulfate and sulfide, and that gives us differences in the metal sulfide values. So in other words, different sulfide minerals will have different sulfur isotope compositions, and sulfate and sulfide will have very different isotope compositions, as we'll see in a minute. We can try and understand the physical conditions of ore formation, so we can derive temperature from sulfur isotopes in mineral systems. We can derive pressure and depth indirectly. And then we can look at the origin and mass of ore-forming fluids, the geometry of plumbing systems, and the duration of hydrothermal activity by using sulfur isotopes. Also, the mechanisms of metal and sulfur transport, and origin and evolutional processes of ore-forming magmas. So there's lots of information that can be gleaned from sulfur isotopes, with an important caveat. Sulfur isotopes, like carbon, are hellishly complicated, and that's because they're so redox sensitive. It's a terrible diagram, but it's from a very good book using geochemical data. And really what it's showing is the range in sulfur isotope values in different reservoirs on Earth. So we see chondritic meteorites, the Earth's core, bulk Earth, and morbs are all around about just slightly negative compared to 0 per mil. Arc basalt, much more positive. As we talked about last time, arc magmas are more oxidizing than, say, mid-ocean ridge basalt magmas. So arc magmas have a lot of SO2, whereas morbs have a lot of H2S. Granite's quite variable. Seawater is around at plus 21 per mil today, but it has varied a lot through time. Marine sediments show a very large range, and that's because of biological activity. And we can see hydrothermal ore deposits also have a very large range, partly because they represent mixtures of seawater, hydrothermal fluids, and biologically mediated reactions. And so if we want to zoom in a little bit on ore deposits, so this is just for different kinds of ore deposits. So we have stuff, VMS deposits on the East Pacific Rise, VMS deposits in Cyprus, VMS deposits in the Kuroko district of Japan, porphyry copper deposits, red bed copper, sediment-hosted massive sulfides, and Mississippi Valley type. So lots of different ore deposit types. And on the left, we've got, so these first three represent medium temperature hydrothermal systems. Porphyry copper are high temperature hydrothermal systems. This is sedimentary and Mississippi Valley are relatively low temperature systems. And so what do we see? We see the medium to high temperature systems tend to have, slightly positive values. Sedimentary systems have more variation. And these Mississippi Valley type have really high variation, and that's because of biological activity. So this is partly why it's so complicated, is there's such a range of potential sulfur isotope values. So what this diagram shows is it shows time in billions of years versus the sulfur isotope value, so the ratio of 34 to 32 relative to the standard. And so we have sulfate in this blue curve, and this is what the ocean water has done for the last billion years. It's gone up and down and up and down in sulfur isotope value, so it's about plus 21 per mil today. So as an aside, the question becomes, well, why has it gone up and down like that? And this has a lot to do with plate tectonics. So the competition between uplifted mountains and seafloor spreading. So when there's lots of seafloor spreading, we drag the values down to mantle-like values or towards mantle. And when there's lots of mountain building, we get more crustal values. And because sulfur gets shed off the crust and goes into the ocean, and so it will drag the ocean values upwards. So the dots and the squares represent sulfate and sulfide from ore deposits. And so we can see that the sulfate values tend to follow seawater with some anomalies, which has to do with fractionation. And the sulfide tend to be much lighter. And that lighter is because in most ore deposits, we're mixing between seawater sulfate and mantle sulfide. And so if we reduce seawater sulfate, we get much lighter values. Okay. And so this is an example of using sulfur isotopes in mineral exploration, and this is for groundwaters. And so Patrice de Caratat did a large study. It's an older study now, but it's around the Broken Hill deposit in Australia, and which is a really important ore deposit district. And so the map on the left just shows where we are in Australia, in the Murray Basin, and the map on the right, you can see the black star shapes are all the mineral occurrences throughout this area. You can see there's a huge number of mineral occurrences. And so what do we see? The red symbols, where it's red, that refers to higher copper and higher zinc concentrations and relatively light sulfur isotopes. The yellow symbols are low copper, low zinc, and relatively heavy or more like ocean water sulfur isotopes. And so close to the mineral occurrences, the groundwater sulfur isotope compositions are more like the deposit values and coincident with high metal values. And this is a compilation from northern Chile, so related to porphyry copper deposits that a former student of mine put together. And basically we have the amount of sulfate in groundwaters on the y-axis, and the sulfur isotope value of sulfate in groundwaters on the x-axis. And the purple field here represents the sulfur isotope values of sulfide minerals in the ore deposits. And really what this graph is showing is as we interact with groundwater interacts with ore deposits, the amount of sulfate goes up because we oxidize sulfide to sulfate, and the isotope value goes down because the groundwater takes on the isotopic value of those sulfides. So again, it's a potential exploration tool. What about sulfur isotopes in magmatic deposits? So these are magmatic deposits, which we'll talk about more in coming weeks. These are deposits that don't form from a hydrothermal fluid, but form directly from magmas. And so sulfur isotope values vary from deposit to deposit, from deposit to deposit, and commonly are around near zero or mantle-like values. The ores and the host rocks at most deposits have similar sulfur isotope compositions or form mixing trends with crustal sulfur. And the reason for this is to make a large sulfide deposit from a magma, we need to bring in external sulfur because magmas can't carry a lot of sulfur. If they did, it would form sulfide minerals and they would precipitate very low in the crust and we'd never form a deposit near surface. So we can look at some values from the Thompson nickel belt in Canada, which is a large nickel copper series of deposits. And we have sulfur selenium sulfur ratios on the y-axis and the sulfur isotope value on the x-axis. The details aren't hugely important, but mantle value is this green box. The red box represents the ores, and the blue box or the blue blob represents sulfur isotope values of sulfides in sedimentary rocks, so not related to ore. And so basically the ores represent, the sulfur represents a mixing of mantle and sedimentary sulfur, and we can see that isotopically. Now we can look at the Bushveld igneous complex, which is in South Africa, and we can see a similar thing. So this is some data that a student of mine did some years ago. The yellow bar here represents the sulfur isotope values of least contaminated massive sulfides in the Bushveld, or sulfide minerals in the Bushveld complex. On the right, so this is some data that he did for a drill hole going down into the country rocks in part of the Bushveld. And so what we see on the right, ignore the red line, but the symbols represent metal values of platinum plus palladium plus gold plus rhodium. You see the metal values are highest in here, and that's where the sulfur isotopes start to go up, become more crustal-like. So there's a relationship here between mineralization and mixing of sulfur from mantle source and sedimentary sulfur source. Okay, now very quickly, John has a question.
Yeah, it's probably a stupid question, but by looking at these sulfur isotopes, you don't really know what metal or mineral is causing it, do you? It could be any one of a variety of them.
Well, you know that in these kinds of magmatic deposits, there's some main sulfide minerals that are.
Actually, I was thinking before the magmatic ones, like when you were looking at I can't. Was it Thompson Creek, maybe, which was
Thompson Nickel Belt,
or even the one before that. I mean, I couldn't tell whether that would be caused by copper or antimony, or whatever.
These are nickel copper deposits. So the sulfides are going to be pyrrhotite, which is an iron sulfide, chalcopyrite, which is the copper sulfide, pentlandite, which is
I just meant if you were like looking in streams and you saw an anomalous sulfur ratios.
Right. You wouldn't necessarily know what mineral it came from. No.
Yeah.
But we do know that ore values tend to be isotopically lighter than surrounding rock values. And so, as you know, if you're looking at it, so if we took this one here, if you were collecting a series of groundwaters in northern Chile, for example, and you found a bunch of heavy isotope values, you'd probably say, well, there's no point carrying on. But if you found a series of groundwaters that became isotopically heavy, lighter and lighter, and sulfate values increased, then you start to get interested. Does that make sense?
Yep.
Yeah. Perfect. Okay, so very quickly, just a couple of examples of non-traditional isotopes. This plot just shows some of the variation that we see in different isotope values. And over on the left, we have oxidation state. So most of these are redox sensitive. So iron's redox sensitive, copper is redox sensitive, zinc is not, so it doesn't fractionate very much. Selenium is redox sensitive. Selenium behaves a lot like sulfur, and so on and so forth. So we're just going to focus in on copper and thallium. So here's a plot that another grad student of mine put together a couple of years ago. And the idea here is to show how copper isotopes are varying as we go from, say, hypogene mineralization in a porphyry copper deposit. And we have the supergene blanket and the leached cap, which Bob's shown an image of several times in different lectures. And so we can see the heavier copper value, copper 65, tends to go into secondary precipitation. The lighter copper tends to go into plants, and so on and so forth. And so copper can get partitioned into different reservoirs as a function of different geochemical processes because it's redox sensitive. And so I'm going to show an example from Chile. So this is just showing the Spence deposit in Chile. The Spence deposit is a fairly large deposit. I forget what it is, 400 million tons or something like that. So it's reasonably large porphyry copper deposit. And these are just some cross sections showing where the samples are from. But what it has the blue is the hypogene ore. The red is the supergene enriched ore. And then the green is the oxide blanket with leached cap on top. And so we have a whole series of minerals that were analyzed. So we analyzed chalcopyrite, which is the hypogene mineral, chalcocite, which is the supergene-enriched sulfide copper sulfide. Chrysocolla and atacamite are secondary copper oxides and chlorides. And so we can see that we measured quite a range in copper isotope values. And then we also determined the age. And so we start off with chalcopyrite, and we weather that to form our supergene-enriched fluids. That copper travels down, so we preferentially remove the heavy copper, and that reprecipitates as chalcocite. Fast forward through time, we've continued to weather this deposit, and we've made a nice supergene blanket with a leached cap on top. So from that chalcopyrite, we form atacamite, which is a copper chloride, and there's a large fractionation. So in that case, the light copper preferentially was preferentially retained in the sediments overlying the deposit. That atacamite was then altered by fluids to form chrysocolla. And again, there was a large fractionation where the heavier isotopes went into the fluid. So in this case, the copper isotopes sort of allowed us to understand the geological formation and history of the Spence deposit. In another case study, this is the Pebble deposit, which is in Alaska. It's quite a controversial deposit because it's very large and potentially very economic, but there's lots of environmental issues, including threats to salmon fishing and First Nations. Nevertheless, the dots represent a series of stream samples and groundwaters that were taken around the deposit. And this is the upshot. So the open symbols are proximal to the deposit, and the closed symbols are far away from the deposit. And the point is, as we get further and further away from the deposit, the copper isotope values become more negative. Also, the copper concentrations become much lower. So again, we have a potential vector to mineralization. And then finally, non-traditional isotopes, thallium isotopes. I'm not going to go through this figure. It's just to show that there's a large fractionation in thallium isotopes, except that you'll notice it's not in delta notation, it's in epsilon notation. So delta notation was in per thousand, epsilon notation is in per 10,000, because the numbers are even smaller. So we had a different student do some work in Nevada. So this represents a drill hole and a series of drill holes going through a gold deposit in Nevada. And what you can see is the hotter colors and the bigger symbols on the left are the thallium isotope values. The middle one is the thallium concentrations, and the right-hand one is gold concentrations. So the red colors are hotter, higher gold, higher thallium, heavier thallium isotopes. So again, we see this nice variation where we have low thallium isotope values away from the deposit and higher thallium isotope values, higher thallium concentrations, and higher gold concentrations within the deposit. And then we did some, or Jeff did some laser mapping of the samples and the upper four squares. So we have the image, optical image, and then thallium concentrations, potassium concentrations, and sulfur concentrations. And what you see is the high thallium in the upper panels corresponds to high potassium. And that's because thallium there is behaving like an alkali, and so it substitutes for potassium into minerals like illite and muscovite. On the lower one, you can see that thallium, high thallium, heavier thallium isotopes, and is mismatched with potassium and matches nicely with sulfur. So in this case, we see that in the upper panels, the thallium is in the silicates and it's isotopically light. And in the lower panel, the thallium's in the sulfide minerals and it's isotopically heavy. Okay, so what have we learned? I think we've learned that isotopes can be powerful tools in mineral exploration and ore deposit studies. Isotopes are critical for understanding fluid sources and transformations as we go from different reservoirs. We can use isotopes to vector demineralization. We can use a variety of possible media, waters, rocks. We didn't talk about it, but we could use plants. We can use individual minerals and so forth. We didn't really talk about fit for purpose analysis, but basically what that means is use the right isotope to answer the right question. And our non-traditional isotopes, maybe they're the future for mineral deposit studies and mineral exploration. But we need to do more research, which means we need more funding. So that's it.